a spring mass system that that has dampening as well as a driving force. So it's a problem like I want to do here. All right. So let's take a look at this problem here. Let me do one thing here.
Can I get permission to record?
Is that okay? Who just spoke?
Connor.
Connor, that's what I thought. I thought it. Where are you? Here you are. About to record. Okay. All right. So let's take a look at this problem here. We have one slug. So we're told what the mass is. All right. The mass is one slug. It's, okay. So let's see. All right. So the mass is one slug. M is equal to 1, and we're told that the dampening offers that's numerically equal to 2 times the velocity, 2 times the instantaneous velocity. So remember now, our beta is equal to 2. Remember now, our differential equation is m x double dot plus beta x dot plus k x, right? Kx is equal to and then we can have some driving force that's a function of time. All right, so this is our, let's see. Yeah, so this is what our differential equation looks like. So we have what m is, and this problem, they tell us what m is, they tell us what beta is, and they tell us what k is, right? K is equal to, they tell us what, k is equal to 5 pounds per foot, okay? Now, I just took a look. The problem that you have on the exam, I'm really trying to help you out here now, especially for the students that come, is that you're gonna have to calculate what K is. All right. So so let's see. Let me take a look at the exam. You know, being this is not a course in physics. Okay. So this is not this problem, but if I tell you have a mass of one slug, right? You have a mass of one slug, and it stretches a spring 2 feet. So in other words, our X or S, I think we use S when we stretch. When we stretch the spring 2 feet, okay, what's the spring constant? Okay, now here we're given the mass, right? We're not given the weight. So the weight, right? The weight is going to be equal to the mass times G. So this is going to be one slug times 32 feet per second squared, right? And then, okay, so that's the weight. And we're told that this is pulled down 2 feet, right? It's pulled down 2 feet. So, so in this case here, it's pulled down 2 feet. So, just want to see something here. Why is beta? Okay. Oh, I was looking at a different problem. I was looking at the problem you have homework. I mean, the problem that's on the exam. So, so I want you to understand that when the mass is 2 slugs and you push it down 2 feet, that the weight is 32, right? The weight now is 32, right? The weight is 32 pounds, right? The weight is 32 pounds. So the spring constant is going to be, the spring constant K is going to be the force which is being supplied by the weight, 32 divided by 2, which is 16. So the spring constant would be 16 feet, 16 pounds per foot, right? £16 per foot. Okay. All right. So make sure you understand this. You do need that for the exam. All right. So now back to this problem here. All right. All right. So we have a mass of one slug. The dampening factor is 2, right? The spring constant they tell us is 5 pounds per foot, right? And what else? Well, we know that at time t equals 0, let's see, it says it's released 1 foot below, right? 1 foot below. So that's positive, right? Remember, we take the positive direction to be down. So 1 foot below. And then it's also the velocity, right? They also tell us that the velocity is downward at 3 feet per second. So this is our velocity, our initial velocity, all right? So this is the initial conditions, all right? And they also tell us that the driving force, let's see, they tell us what the driving force is here. Okay, this one is not, oh, okay. Yeah, they tell us that the driving force, it's given down here. The driving force is equal to 8 cosine of 2t plus 2 sine of 2t, right? So that's the driving force. Okay, so now we have everything, all right? So, so my differential equation is x double dot plus 2x plus 5x, right? And that's equal to 8 cosine of 2t plus 2 sine of 2t. Okay, so, all right. So now I have everything. So let's see. So the first thing I'm going to do is I'm going to solve the homogeneous differential equation, right? I set this equal to 0. And let's see. So this, my auxiliary equation or characteristic equation, this becomes m squared plus 2m, right, plus 5 is equal to 0. And this is not factorable. So let's see. So I'm going to use the quadratic equation. Let me know if I go off the page. I'm going to use a quadratic equation that m is going to be equal to minus, let's see, this is minus 2 over 2 plus or minus the square root of 4. And then this is going to be 4 times 1 times 5, right? Divided by 2a. So this is going to be minus 1 plus or minus the square root. Let's see. Okay, so this is 20 minus 4, so this is going to be minus 16, right? This is minus 16 divided by 2. So this is going to be minus 1 plus or minus, this will be 4, right? This is going to be a 4i divided by 2. So this is going to be minus 1 plus or minus 2i, right? So the solution to this the solution to our homogeneous differential equation is, right, this is the complementary solution. It's going to be C1, and I guess I'll put the exponential up front. C1 e to the minus t. Well, let me just see something for a second. Yeah, I think it's I'm going to put the exponential out front. So I'm going to write this as e to the minus t, right? And this will be C1 cosine of 2t plus C2 sine of 2t. All right. And what would be the transit term, right? If I actually, we're going to have something else here, which is we're going to get a steady state term when we apply the particular solution. But this whole thing is the transit term. Don't tell me that I'd have to mark it wrong. Don't tell me that e to the minus t is the transit term, right? This is the transit term, the whole thing, because everything here goes to 0, right? When t goes to infinity, this whole thing goes to 0, all right? And if you had something like this, right? If I ask you what the transit term is, don't tell me that the transit term is this. I have to mark it wrong. It's the whole thing, because this is multiplied by this. So this whole thing goes to 0, right? This whole thing goes to 0, not just this. Okay. So so you do have questions about what's the transit term and what's the steady state term. So I want everybody to get this right. Okay. All right. So, all right. So now, now notice here I have a 2t, and here I have a 2t, right? And here I have a 2t. But this whole thing here is multiplied by e to the minus t, right? So this is linear independent from this, right? In other words, if I didn't have this e to the minus t here, right, I couldn't I can assume a particular solution looks like this: a cosine of 2t plus b sine of 2t, right? I can assume a particular solution that looks like this. Because I have this e to the minus t here, right? If I didn't have this e to the minus t, right, and this was c cosine of 2t, and this was c sine of 2t, I couldn't assume a particular solution like this, because this would not be linear independent from this, right? Okay. All right, so let me go to another. So now let's get another sheet of paper here. So okay, so now I'm going to assume that this is my particular solution. And then I'm going to take the first derivative. So this is going to be, let's see, this is going to be minus 2a sine 2t plus, this is going to be 2b cosine of 2t, right? And then the second derivative, this is going to be minus 4a, right? Cosine of 2t minus, this is going to be a minus, right? This is going to be minus 4b, and then this is going to be sine of 2t, right? So that's my first and second derivative, and I have to plug it into this equation here, right? I got to plug it into. I'm just copying down. Okay, so I got to plug it into this equation here. So let's see. So what's the best way to do this? All right, so I'm going to get now let's see. Now I'm multiplying this by 2, so I'm going to get this is going to be a minus 4, right? Minus 4a. Right, I see this is a minus 4 because I got this 2 here, right? And then this is going to be a plus 4b cosine of 2a. Now let's see. Okay, now I also have a plus a cosine of 2 of t plus b sine of 2t, right? And this is all equal to 8 cosine of 2t plus 2 sine of 2t, right? Does that look right? Okay. All right. So now let's so here I got cosine, here I got sine. So let's combine. Let's see. Here I got a minus. Here's a cosine. Let's see. Here's cosine. Here's cosine, and here's cosine. Right. So let's see. So this is. Let's see. This is okay. See. This is oh, this is multiplied by 5. I knew something wasn't right. How come nobody caught me? This is multiplied by 5, right? I forgot this here is multiplied by 5. So this is going to be a 5a, right? And this is going to be 5b. right? This is phi b, right? I forgot to multiply by this phi. Okay, now it's making sense. Okay, so let's see. So, okay, so what do I have now? Well, for the cosine, okay, this is going to, let's see. Okay, so I get a 4, here I got the 4b. Here I got a minus 4a. Okay. All right, let me, I can write this as minus 4a plus 4b plus 5a, right? I'm just looking at the cosine terms. And then and then this is going to be cosine of 2 of, right? And then the sine, okay, for the sine, I got, let's see, minus 4b, I'll do it this way, minus 4b, minus 4a, minus 4a, right? Minus 4b, minus 4a, plus 5b, and that's equal to the sine. I could have, and all of this, right? All of this is equal to, put the equal sign here, is 8 cosine of 2t plus 2 sine of 2t. Okay. All right. So I was going to do this. I was trying to decide. So whether I should do it all in one step. So now here I got a minus 4a, and here I got a plus. So this is going to just be a, right? This is just going to be a plus 4b, right? This will be a. I can write this as well, 4b, 4b plus a is going to be equal to 8, right? This is going to just give me this is a 4b here, and then this is going to give me an a, right? I got the 5a and the 4a, so that gives me an a, and that has to be equal to 8, right? Because I'm matching, right? We're matching the coefficient that's in front of the constant that's in front of the cosine with the constant that's here, right? So I get a 4b plus a is equal to 8. Now here I can simplify this, right? I can get minus 4a plus 5b, right? Plus 5, no, minus 4a plus b is going to be equal to 2, right? Right here I got a minus 4b, here I got a 5b, so it's okay. So these are my two equations, right? Those are my two equations. So let's see now, what's the best way to solve these? Let's see. If I multiply this equation, I'm going to multiply, so there's more than one way of solving this, right? I'm going to multiply the top equation here by 4. So in other words, I'm going to write this as 4b plus, no, multiply by 4. This is going to be 16b, right? Multiply this by 4. This is going to be 16b plus 4a is equal to 32, right? And this equation I'm going to leave alone. Minus 4a plus b is equal to 2. If I add these two equations, right, I'm getting that this cancels out, and I'm getting the 17b is equal to 34, right? 17b is equal to 34. So then b, so then b is going to be equal to 2, right? B is equal to 2. So now I got the b is equal to 2, right? I got b is equal to 2. So let's see. So minus 4a plus 2 is equal to 2. Okay, so I get minus 4a is equal to 0. So a is equal to 0. So in this case here, a turns out to be 0. Okay, so now we get another sheet of paper. So So remember now, my particular solution A is equal to 0, right? So
I don't, Professor,
yes,
I didn't get B is equal to 2 and A is equal to 0.
what's that?
I did not get B is equal to 2 and A is equal to 0.
What did you get?
Well, I got A is equal to 3/4 and I haven't solved for B yet, but if you plug B is equal to 2 and A is equal to 0 in those equations, they don't work. Maybe I have it wrong.
Most of my, do you have the same equations that I have?
Oh, I think I must have switched around what I was plugging in. Sorry.
Okay. Well,
Yeah, you're right. You're right.
yeah, I'm looking at my notes and my notes have the same result. My notes got the right answer. Okay. But that doesn't mean I didn't make a mistake. Okay, so, all right, so, a mistake that students make, and it's a minor mistake, I know, is that, okay, we got A is equal to 0. So remember that the A is in front of the cosine, right? And the B is front of the sine. So don't mix up your A and B. So my particular solution right? The A is equal to 0. That was in front of the cosine. So my particular solution is that it's 2 sine of 2t, right? That was my particular solution. Remember, our complementary solution was e to the minus t times c1 cosine of 2t plus c2 sine of 2t. Okay, so our total solution, right, is the sum of these two. So our total solution is e to the minus t c1 cosine of 2t plus c2 sine of 2t plus 2 cosine of 2t. All right, now remember now, our initial condition was that at t equals 0, this is equal to 1, right? It's below, it's 1 foot below. So this is going to be 1 now, and this is going to be 0. This is 1. So this is, let's see, when I put 0 in here, this is going to be C1. And this is 0, right? When I put 0 in here, I get 0. Sine of 0 is 0, and this is 0. So, so C1 is equal to 1, right? C1 is equal to 1. Now, we're also told that x dot of 0, right, was equal to 3. Was equal to 3, all right? Now, this is why I think it's easier to write it like this when you take, because we have to use the product rule here, right? So let's see. So I'm going to take the derivative of this. So this is going to be e to the minus 2t, and I'm going to leave this alone. Then let's see. Then I got a plus e to the minus t. Now I'm going to take the derivative of this. So this is going to be minus 2c1, right? Sine of 2t. And then this is going to be, I'm going to have a plus here. This is going to be a plus 2c2 cosine of 2t, right? And the exponential times everything here. And then let's see. And then it's going to be plus 4 cosine of 2t, but this is going to be a minus. Yeah, so this is going to be a minus. Okay. And this all has to be equal to 3, right? This is equal to 3. So, okay, so I took the derivative. Now, when I put 3 in here, right, I put 0 in here. So this is going to be minus C1, right? This is going to be 0.
Professor?
Oh, yeah, wait.
Or cosine of 2t minus.
Hold on 1 second. This is, well, I didn't take the derivative of this, right? I'm just taking the, this is right. There's something wrong here?
The last minus, isn't it supposed to be plus?
Oh, right. That's plus. Right, take the derivative of, right, that's right. Okay. So, all right, so now when I put 0 in here, okay, so this is 3. This is going to be, okay, C1 is equal to 1. All right, I think something's bothering me here. Okay, here I'm getting a minus C1. Okay, what's this here is, this is 0, right? When I put 0 in here, this is 0. This is 0. And this is going to be a plus 2C2. And then this is 4. Right? Right? Everybody agree with me on this? This is going to be a minus C1 here. This is 0. This is 0. When I plug 0 in, this is going to be 2C2. Right? And this is 4. Okay. Now we got C1 to be equal to 1, right? So this is telling me that C1 is equal to minus 1 plus 2C2 plus 4. So this is telling me that that 4 right, okay, so this is telling me that C2 is going to be equal to 0. Right, so C2 is equal to 0. Okay, it's not going to matter. C2 is equal to 0. Right, when I bring this over to here, right, so C2 is equal to 0. Okay. All right. Any questions? Everybody agree that C2 is equal to 0? Right. I bring the minus 1 over here and the 4 over here, so then I get 0 on both sides, and C2 is equal to 0. Okay. All right. So so now what? All right. So now we're done. Right. We're done. My final answer, right, is going to be e to the minus t cosine of 2t plus 2 sine of 2t. Okay, so that's it. That's the final answer. Okay. Any questions on this problem? So you will have a problem like this on the exam. And just to help you out too, on the exam though, you're gonna have to figure out what K is. Okay, you're gonna have to figure out what K is, like I did here. So I'm basically telling you that this will be on the exam. We have to figure out K in this way. All right, but I don't know if those are the right numbers. All right, let's see what time we got. Okay, let me there's actually an error. I noticed that there's let's see. Give me a second here. Okay. I just want to go through my notes. I guess you see my notes now. I'm sharing the screen. This is what confused me. There's an error in my notes. You see this here? This should be a -1. Right? This should be a -1 here. So I'll fix that. Yeah, this should be a -1. And the other thing too is that I must have did it in my head. You can quickly see that if we put in the initial condition, right, that at time t equals 0, x is equal to 0. I didn't actually show that, but I took C1 to be 1. Okay, because if you put 0 in here, then right, then this is 1, right? This is 0, right? This, when you put in the initial condition for the position, this is 0 and this is 0, and then this is 1. So you, and then this is 1. So you're getting that 1 is equal to C1. But this here should be negative. This should be negative here. And then that makes C2 0. Okay, so I got to fix that. Okay. All right, I want to do any questions? Yeah, so and just let me show you the reason why I went here too is I wanted to show you the graphs. Okay, so this is the total solution. This here is the total solution, and that's what we have here, right? This is the total solution. When you add these two together, this is what you get. So you had to pick that, and I guess that's oh, okay. So once again, now this is the particular solution, right? And this is the complementary solution, but the particular solution is also the steady state, right? You know, when you take a look at this, hope everybody sees what's on the screen, right? When you take a look at this, here's the steady state, right? And here's the transient, right? So the transient dies out, right? The transient dies out, and here's the steady state. And so those are the two solutions. So I graphed them using, I graphed the solutions using Desmos, right? So once again, the particular solution is the steady state, and the complementary solution happens to be the transit. It could be the reverse. You can get problems that are reverse. Okay, so I want to do a spring mass system. Excuse me, I want to do an RCL circuit. I guess maybe I'll do this one here. Let's do an RCL circuit problem. Go back to. Okay. So here are the graphs. You take a look at these solutions here. All right, so here's an RCL circuit problem. Guess I'll use the other side here. Okay. All right. So this is the, let's see, that's the anti. So for an RCL circuit, right, the differential equation is this, where this is the charge as a function of time. Now, in this problem here, the voltage was just constant, okay? All right, so that's our differential equation. And it's the same for a spring mass system, all right? So now let's see. let's see how to, let's solve this problem here. All right, so we're told in this problem that L is equal to 5/2. R is equal to 10. C is equal to 1/20. And the voltage is actually a constant. It's they give it as a function, but it's equal to 40, right? All right, so let me try to. And what else do they tell us? They tell us that that the charge, right? They also tell us that Q at time t equals 0 is 0, and that the current is 0, right? They tell us, okay, and then the current is also 0 at time t equals 0. So this is just like in a spring mass system. This would be position, this would be velocity, right? This is just, remember now, the derivative of Q is just I. Okay, let me just see something here. What problem is this? I think there was 2 RCL circuits. This is 3. Yeah, okay. Now, you know, you had a problem just like this in the Weber sign, but you maybe with different numbers. Okay, all right. So let's see. So so this is just going to be 5 halves Q double dot. I'll save some writing. Plus, let's see, the resistance is 10. Plus 20. No, plus yeah, C is 1/20. All right, so yeah, so this is going to be 20 Q. Okay, and that's going to be equal to 40, 400. Okay. You see 1/20? Yeah. Yeah. C is 1/20, so therefore 20 is equal to 1/C, right? I got 1/C here. Okay. All right, so let's see. I think the best way to do this is to let's see. Well, I can rewrite this as Q double dot, and then multiply everything through by 5. Yeah, if I multiply the entire equation, it's more than one. If I multiply the entire equation by 5/2, then this is going to be Q double dot plus, see, this will be 20, and then divide that by 20 divided. So this is going to be 4 Q dot, right? 20, then divided by, and then this is going to be, let's see, this will be 8, right? This, let's see, this divided by this is going to be 4, and then times 2. So this is going to be 8Q. And then this is going to be 160Q, right? All right, this divided by this gives me 80, and then times 2. All right. All right. So all right. So now everybody with me up to here? No problems. All right. I just multiplied the entire equation by 2/5, and I got this. Right. So now I'm going to say this is m squared, right? My auxiliary equation or my characteristic equation. Then this is going to be 8. Right. So first thing I'm doing is I'm solving the homogeneous differential equation. Right. So let's see. So this is going to be m is equal to, now this will be minus 4/2, right? So this is just going to be a -2, right? So -2, right? 4/2 plus or minus the square root. And then this is going to be 16 minus 4 times 8 times 1. So that's going to be 32 over 2. So there's going to be minus 2 plus or minus the square root. Let's see. So this is going to be 6. This is going to be minus 16i divided by 2. So this is going to be minus 2 plus or minus 2i, right? When I factor this out, I don't really need to put the I there, right? 16 I can factor into 4 times 4, right? 4 squared, so that makes that 4, and then I divide by 2, okay? So that's it. So now my complementary solution for the charge as a function of time is going to be equal to, so it's very similar to the other problem. I think I did it intentionally, so you see that that the math is the same whether we're dealing with spring mass systems or we're dealing with RCL circuits. Right? So that's my complementary solution. Okay. Now, what do I, this is just a constant, right? This is just 400, right? So I'm going to use this equation here. And what am I going to assume now? Let me know if I go off the page. What am I going to assume for my particular solution? Well, my particular solution, I'm just going to assume that, that this is equal to A, right? I just have a constant here. All right, I don't have any constant. Now, if I had a constant in the solution, in the complementary solution, if I had a constant here, I have to assume T times A, right? But I don't, so I can just assume a particular solution of A. So this is going to be pretty easy. So so that's just 0, right? So Q dot is 0, and then Q double dot, why am I putting A, is also 0. Right? It's also 0. So once again, just to okay, so now this is 0, this is 0, so I'm just getting here that 8A is equal to 160. So that means that A is 20. Okay, so A is 20. So all right, so my total solution, I guess I can fit it down here. My total solution is e to the minus 2t c1 cosine of 2t plus c, this should be a 2, c2 sine of 2t plus 20, right? This is my complementary solution, and this is my particular solution. And so this is my total solution. Okay. All right. So all right. So now we have to apply the initial conditions. So let me do this. Let's see. Everybody can see what I'm. Okay. So all right. So let's see. So now, okay. So now let's see. Q of 0 is equal to 0. That's what we're told in the problem. So when I put 0 in here, I'm going to get 0 is equal to, this is just going to be 1. So, and yeah, this is going to be 1. So C1 plus 20, right? We can't forget the plus 20, right? This is 1. This is 1 cosine of, when I put 0 in here, and this is 0, right? This is 0 when I put 0 in here. Is everybody okay with this? So I'm getting that C1 is equal to minus 20, right? C1 is equal to minus 20. Right? This is 1, this is 0, and I got the 20 here. Okay. Now, all right, so now I got to take the derivative of this. And so let's see. So I'm going to get minus 2 e to the minus 2t c1 cosine of 2t plus c2 sine of 2t. All right, I'm using the product rule here. Then let's see. And then I'm going to get, I guess I'll put it down here. Then I get e to the minus 2t. And then this is going to be minus 2c1 sine of 2t, right? And then it's going to be plus 2c2 cosine of 2t. And the derivative of 20 is 0. Okay. So now, remember now, this is the current, right? This is the current. And we're told that at t equals 0, this is also 0. So I got 0 is equal to minus 2 c1, right? This, when I put 0 in here, I get c1. This is 0, right? And let's see. And then this is 0. This is 1. So I'm going to get a plus 2 c2. All right. Everybody with me on that? Okay. All right. So this is telling me that, right? This is telling me that c1 is equal to c2, right? If I bring this over to this side and cancel out the 2's, right? It's telling me that c1 is equal to c2. And we found what c1 was. C1 was minus 20. All right, C1 was minus 20, something, C2 is equal to 20, right, because they're equal to 0. So C2 is equal to 20. Something, so C1, so C2 is equal to 20. And C1, yeah, C1 was equal to minus 20. They're both equal to minus 20. I think I have another error in my notes. C1 is equal to C2. I left out the minus sign. Okay, so our final answer, now I got C1 and C2. So my final answer is e to the minus 2c plus minus 20 cosine of 2t minus 20 sine of 2t. That's it. Plus, yeah, plus 20. Okay. All right. So that's our final answer. Let me take a look at my notes. Okay. All right. All right. So in my notes, I didn't. It's right. Okay. It's right, but there should be a minus sign here. This should be a minus sign. See, sometimes when I copy and paste, it's all right, but there should be a minus sign here, right? Because yeah, C1 is equal to minus C2, but there is no minus sign here. There should be a minus sign here. Okay, but the answer, yeah, the answer is right. There should be a minus sign here. Okay, and I wrote it differently. All right. Now the next part of the problem is just to calculate the Any questions before I go on? Right, so this is the final answer. Wonder if it's easier to write it in a different way. Let's see, where are we? Okay. Okay, so so to calculate the current, you just take the derivative, right? I just take the derivative of this to calculate the current. So I guess we could do that, right? Remember the current I is just, well, we already did it up here, but now with the numbers in here, we can calculate what the current is as a function of time, right? So this would be, let's see. Well, I could, I wrote it like this. It's going to be in a different form than my notes. So let's see what happens. I get e to the minus 2t, and then this is going to be 40 minus 40 sine, and then this here is going to be this will be 40 cosine, right? So, and I got to use the product rule. So now here this is going to be a minus e to the minus 2t, right? And then this is going to be minus 20 cosine of 2t plus minus minus 20 sine of 2t, right? Okay. So so let's see. So here we got an e to the minus 2t, and here we got a this is gonna be a minus here. This is 40. So this is gonna make this a plus, right? This is gonna make this a plus. So oh, I gotta put it. I forgot to take. Yeah, I gotta put a 2 here, right? When I take the derivative of this, right? When I take the derivative of this is gonna be a 2. Okay. Okay, so let's see. So what do we got here? So this is going to give me right. So the signs are going to cancel out. The signs are going to cancel out, right? Yeah, the signs are going to cancel out, and then I'm going to be left with e to the minus 2t, and then this is here I got a minus 40. Here I got and then it's going to be this is going to be 80, right? No, the cosines cancel out. The sines will cancel out. So the answer is I as a function of t. Let's make sure this is going to be equal to 80 e to the minus 2t sine of 2t, right? The sine, yeah, the sine is going to, let's see, 0. When I take the derivative of this, this is, this is sine. Yeah, so this is a plus here. Right, when I take the derivative of cosine, it's going to be minus the sine, and I got the minus sign here. So the, yeah. So, yeah, so the cosines cancel out, but this is a plus, and then here I got the minus 2 minus, so it becomes 80, but the cosines cancel out, so that's the answer. Okay. All right. Okay. let me talk a little bit about the exam. So you'll have the exam tomorrow. So tomorrow, tomorrow we'll start power series. Okay, tomorrow we'll start power series, and then after the class tomorrow, you'll be able to download the exam. There's a few things I want to talk about to help you out. I gave a very similar problem the last time I taught this class, where I just want to remind you that, let's say I have a critical point, right? I have a critical point. Let's say the value here is 100. About 30% of my students got this wrong the last time. And let's say it's a stable critical point, so the arrows look like this. Critical point. All right. If I tell you that, let's say we're starting out with 90 something, right? As t goes to infinity, right? It doesn't matter what the differential equation is. It's that if this is a critical point and it's 100, remember that when we have solutions, they're going to go to the critical point. They're not going to pass. They can't. The solution cannot go like this. It has to go to the critical point. So let's say we start out with a population where, let's say we're dealing with giraffes, and let's say that there's an environment where the giraffes, the foliage cannot support more than 100 giraffes. Okay, so if I start out with 90 giraffes, eventually you'll reach 100 giraffes, right? If I start out with 80 giraffes, eventually you'll reach 80, because the foliage could support 80 giraffes. Well, let's say I start out with 90 and I add 40, right? I start out with 90 giraffes and I add 40 giraffes. As t goes to infinity, what's going to be the number of giraffes? I started out with 90, I added 40. What's going to happen? The number of giraffes is still going to go to 100, right? It's going to go to 100. It can't, if we start up here at 90, right? Let's say, if we start here at 90, right? Say 90 is down here, then it'll go to 100. If we start up here, let's say 130. Now there's 130. Let's say we took giraffes from one park to another park, right? And we start up here. That eventually unfortunately, the giraffes are going to die off, right? And we're going to end up with 100 giraffes. So make sure you understand that, the concept of the critical point, especially when you do, like right now we're dealing with populations, but I know a number of you may go into electrical engineering and systems engineering. This is very important for control systems. You want control systems to maintain, a certain level. So make sure you understand that if I start out with 90 and suddenly I add to it, right? Eventually, as time goes on, as time goes to infinity, it's going to approach 100. It's not going to be 130. It's going to be 100. Okay. Okay, so now I want to talk about something else for the exam. Okay, let's see. Okay, hope everybody sees my screen. You can have a multiple tank problem. Now, we haven't learned how to solve a system of differential equations. That's actually what we're going to do. I guess maybe the last 2 days of class, or the last day of class, how to solve a system of differential equations. But you will have a problem where you have multiple tanks and you have to set up the system of differential equations. And if you could, reason why I want to go over this problem, if you could do this problem, you'll be able to do the problem on the exam. If you can't do this problem, then you have a problem with the problem on the exam. But there's a problem on the exam where you have multiple tanks and you have to set up the differential equation. So let's take a look. See, we have this tank A, tank B, and tank C, right? and pure water is going into tank A, right? Now, once again, see, construct a mathematical model for the pounds of salt in each one of the tanks. So we want to find the pounds of salt in each one of the tanks. All right. So first of all, I'm representing the amount of salt in tank 1, and tank A is X1, right? The amount of salt in tank B is X2, and the amount of salt in tank C is X3, right? So so first of all, pure water is going into tank A. So that's just going to be 0 times 6, right? It's 6 gallons per minute. But just to show you, we'll make it clear, there's no salt going in, right? If I look at here, right, it's I got 6 gallons, but no salt is going in. But now from tank B, right, salt is going in. Salt is going in at a rate of 2 gallons per minute, right? And there's 100 gallons here, right? So the amount in which salt is going into tank A from tank B is 2, right, divided by 100 times the amount of salt that's in X, the amount of salt that's in B. So the amount of salt that's in B is just, you know, once again, we're representing the amount of salt that's in B as 2, as X sub 2, right? Now also there's salt coming out of tank A, right, at 8 gallons per minute. So you see the salt coming out of A is 8 divided by 100, and then the amount of salt that's in A, right? And then you can simplify. So then this is, you know, this is just 0, right? And then this is, I can write this as 2 over 100 is 1 over 50, and then 8 over 100. So this is just simplifying this. But if you were to leave it like this on the exam, I'm good with that, all right? And so now the same thing for what about tank B, right? Well, tank B, let's see. We got, first of all, let's see. Okay, so we start out what's going in. Remember, it's always in minus out. So there's 8 gallons going in, right? 8 gallons going in. I think it's pretty straightforward. 8 gallons going in, and then from a 100-gallon tank, right? So, and that's from X1, right? So it's from tank A, which is the X1. I'm getting 8 gallons going in, right? And then let's see. Then we're also getting, let's see, what else is going in? We're also getting 1 gallon's going in here, right? And then the 2 gallons are going out. Here's the 2 gallons going out, right? But they're going out of X, they're going out of B, right? And then we have 7 gallons, right, are coming out from B into C, right? So this is what's going out, and this is what's going in, right? Remember now, what's going in is from A, and what's going in is also from C, and then what's going out is from B, right? Okay, everybody okay with this? So if you can follow this, you'll have no problem doing the one that's on the exam. And then for tank C, well, what's happening with tank C? And it is, let's see, let me take a look at the exam for a second. Yeah, it's the same. In other words, I didn't make 150 gallons and one, they're all 100 gallons. But the problem is a little bit different, but not much. If you, like I said, if you understand this, you'll be able to do the one that's on the exam. Okay, so you see now what's happening with tank C. Well, tank C, right? We got right, we got the 7 gallons going in from tank, right? The 7 gallons going in from tank B, so that's why it is in X2. 7 gallons going in from tank B. And then 1 is going out. 1 gallon per minute is going out from tank C, right? 1 gallon's going out a minute from tank C. And then 6 gallons, and then 6 gallons per minute are going out from 3. All right, so here are the 3 different. This is the system of differential equations that that solve this multiple tank problem. So if we we don't know how to solve this, but we will learn how to solve this at the end of the semester. And it's not hard. It's just a little bit of linear algebra. But
Professor.
here's the system. All right. So this is the system of three differential equations that we have to solve simultaneously. And you can't solve these algebraically. I've had students try to solve these algebraically. It's not the way to do it. You can't do it that way. All right.
Professor,
Yes,
I have a quick question.
sure.
On tanks. So why did for the tank B, why did we set both 7/100 and 2/100 as x2?
Okay, you're talking about the multiple tank problem? Let me go back
Yeah.
to. Okay, what
So for tank B, we set 2/100 and 7/100 as a function of x2. So why is it both has the same variable?
we'll see. Okay, so okay. Because both of them are coming out of X. The 2 gallons per minute here, right? It's coming out of X, it's coming out of B, right? And the 7 gallons per minute is coming out of B. So this is the amount that's in B. X2 is the amount that's in B. Is that your question?
Yeah, but I'm trying to figure out why was it like both of them was x2.
It's X2 because it's coming out of X. It's coming out of B, and we're representing the amount of salt in B as X2,
Okay,
right?
all right.
The amount of salt in A is X1, the amount of salt in B is X2, and the amount of salt in C is X3. Okay.
Now, for example, for the first one, why didn't we set 0.6 and then 8/100 as x1?
Because it's coming out of, okay, what's going into tank A? Tank A, right? The amount of salt, first of all, the amount of salt going in here is 0, right? So that's why there's this 0 here, right? We're told it's pure water. So it's 0 times 6, right? Then here now 2 gallons are going in, right? 2 gallons per minute are going in, and it's going in from B. So the amount of salt that's in B is X2. And there's 100 gallons. So, right? And then what's coming out, see the minus sign here, it's coming out now. Make sure that when it's coming out, you want to have a minus sign. When it's going in, you want to have a plus sign. So with tank A, right, we got this mixture of 100 gallons and it's going out. That's why there's the minus sign. And it's coming out of A. That's why we have X1. Did I answer your question?
All right, yeah.
Okay. All right. Let's see. Okay. So I just want to go over the problems that are on the exam and give you an opportunity to question. So okay, hopefully everybody can see my screen. Okay, so here are the problems that are on the exam. Here's exam 2. Okay, so exam 2. So you have to find a solution to a second order linear differential equation with constant coefficients. Okay, pretty straightforward. Okay, and then find the solution to a second order non-homogeneous differential equation with constant coefficients. All right, and then you have to solve initial value problem with a second order non-homogeneous differential equation with constant coefficients. Right, a population problem. So this is dealing with this population problem, it's well, I'll tell you, it's going to be like a logistics, it's going to be like the logistics equation, and make sure you understand what I talked about earlier. And then there's going to be a tank mixing problem, and I'll give you the I basically one that I did in class. Okay, went maybe with different numbers. Okay, and then a spring mass with no dampening and no driving force. Make sure you understand how to find the period, right? I think I may actually for the period. And then a spring mass system with dampening and driving force, like I did today. And then a multiple tanks problem. Okay. Make sure you use the methods that we learned in class. Like we're required to, I stated in the problem, but there's a requirement that that we learn how to solve linear non-homogeneous differential equations using the method of undetermined coefficients. There's also a method called variation of parameters, and there's also a method called annihilation. So there's 3 different methods, but you need to use the method of undetermined coefficients. And if anyone's interested, I did. We're not going to do nonlinear. Remember, I said if time permits. I actually didn't do it when I had the 15-week class either. Okay. Any questions on the exam? So once again, tomorrow we're going to start power series, and we'll start power series tomorrow, and then after tomorrow you'll be able to download the exam, and the exam will be due back. Let's see, tomorrow's Tuesday. The exam will be back Wednesday night. Okay, exam will be back Wednesday night. Unfortunately, I won't be able to get back the solutions. I normally mark the exams over the weekend. And so you'll get your, well, if you take a look, probably starting on Thursday night, if you look at my grades, you may start to see them, but I probably won't finish them until Monday. And I do the exams in order in which the students submit them. Okay. All right. Well, we still got 15 minutes. Does anyone have any questions on the exam? Any other questions? Everyone's good? Let's see how many. Okay. I hate to waste the time. All right, let me I just want to remind you, let me start talking a little bit about power series. I don't know if you remember, but like the sine, the power series for sine, this was, let's see. Okay. Power series for sine, okay, is equal to x minus x cubed divided by 3 factorial. Remember this, plus 5. If you're going to continue in math, these are power series commit to memory, right? That's the power series for sine. This is actually the Maclaurin series, right? When we just to review a little bit, when we have when we're expanding about x is equal to 0, this is the Maclaurin series, and then the cosine would be 1 4 factorial. Okay, so we have the power series for sine and the power series for cosine. I'll talk, I guess, maybe the next time about the ratio test. But let me see if I can find something here. Give me a second. Maybe I'll get this done. Yeah, I guess we could, remember, I'm just, this is what's in my notes, but if you remember, like, this is the Taylor series, right? Uh, and etc. I guess I'll just do two, right? This is what we refer to as the Taylor series. Right? And the Maclaurin series would be when this is equal to 0. In other words, if I wanted to have, if I was expanding about x is equal to 0, a is equal to 0 here, then this would just be the derivative at 0, and then this would just be x, and then this would be 1 factorial plus 0, and this would be x squared over 2 factorial. This is 2 here. X of 0 over 3 factorial, right? This is what we refer to as the Taylor series. I guess I'll go over this again. But I just want to show you maybe today, and then we'll call it a day, is that, how do I get this? Well, this is our Taylor series, right? And let me start another sheet of paper. Let's see. Let me just calculate. Let me calculate, let's say, the sine of 0, right? This is just 0. All right. Prime, right? This is going to be now cosine of 0, right? And I take the derivative. So this is 1. And then double prime. This is minus the sine of 0. So this is 0. And then I'll do another one. And then this is going to be minus the cosine of 0, which is equal to minus 1. And I guess if we did the fourth, remember when we do the fourth, we write it like that. This would be sine again. And then this would be 0. Okay. So, okay, so if you take this, right, and you put it to the Maclaurin series, remember now the Maclaurin series, and I could actually derive the Maclaurin series too. I could show you where this comes from, but maybe we'll skip that. This is the first derivative. This would be the second derivative. I'll do one more. Etc. Okay. So here now, if I want the sine, if I wanted the sine of x, right, expanded in terms of the Maclaurin series, right? Well, first of all, this is 0, right? This is 0. Now this is 1, right? Now this is 0, right? This is 0. And then this is minus 1. So I get minus 1. So this would be x cubed over 3 factorial. And then, okay, and then the fourth one is 0, right? So this is, I'm going to have a 0 here. And then the fifth one, which I didn't do, let's say the fifth, this would be 1 again, right? This would be the cosine of 0. And I take the derivative of that. This would be the cosine of 0, which is 1. So, okay, so this is 0. So then this is going to give me x to the fifth divided by 5 factorial, right? So I'm just showing you that that the sine, right, the sine of x, another way of writing the sine of x is in terms of the Maclaurin series, right? The Maclaurin series is about x is equal to 0. And so, so this is it, right? This is what I had before, right? So the sine of x, another way of writing the sine of x is x over 1 factorial minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial. Okay. You know, another way of writing this now is that, you know, I can write this as a summation. So we did 2n plus 1 divided by 2n plus 1 factorial. Right? So this is the sine of x. Okay. Let's see. One of the things, I guess I'll do this tomorrow. Won't be able to finish it today. All right, but one of the things that, so we're going to start on power. We'll do some more power series tomorrow, more review tomorrow. But one of the things I want to do tomorrow is I want to solve like this differential equation here. Everybody should know that the solution to this differential equation is, right, this would be, I can write a C1 cosine of x plus C2 sine of x, right? Not x. Let's say this is t. Oh no, let me. I probably should have wrote it like this. Let me use y. Let me use y. Okay. That and I'll put x in here. So the solution to this differential equation is C1 cosine of x plus C2 sine of x, right? Because, you know, this is our characteristic equation, right? When I bring this over to here, I get plus or minus I, right? And plus or minus I is going to give me, this is my solution. One of the things I'll do tomorrow is I'll show you that using power series method, that I'm going to, indeed, if I use a power series method to solve this differential equation, I'm actually going to get solutions that look like this for sine and for cosine, right? I showed you what cosine was before. So anyway, we'll start doing that tomorrow. And I just wanted to remind you, you know, what the power series for cosine, the power series for sine looks like. We'll take a look at the cosine, you know, e to the x, right? E to the x is 1 plus x squared divided by 2 factorial plus x to the cube divided by 3 factorial. These are power series that if you continue in math, you should actually commit to memory. Okay, just one last thing. When I first learned about power series, one of the things that I found amazing is that what is it really telling you? Like when you look at this equation here, when I look at this equation, right? It's actually telling me that if I know a function at just one point, right? If I know a function at just one point, and I know all its derivatives at that one point, that's the same thing as knowing the function everywhere. And that's what we actually call an analytical function. All right. If you know the function at one point and you know all its derivatives at one point, right? See here, I just know the value of the derivative. See, I know the derivatives at just one point. The point I picked was 0. So I know the function at one point. I know all its derivatives at one point. That's exactly the same as knowing the function everywhere. I found that amazing when I first learned about power series, probably 45 years ago. Okay, that's it for today. I do want to start solving the power series problem, but I probably won't be able to finish it. So, but I'll stay on if anybody has any questions. And if you have questions, the exam will be tomorrow, but if you have questions tomorrow about the exam, you could, I'll be happy to answer any questions tomorrow as well as today. But that's it for today. And I'll see you all tomorrow. You can stay on if you have questions.
Thank you, Professor. You have a great day.
Okay.
Professor, can I quickly see again the multiple tank problem? Because I wasn't able to see it on any of the.
Oh, you
any
weren't
of
able
the-
to see it? Okay.
on the web, not on the what's it called again? The Blackboard.
You can see it now?
All right.
It's
Yeah.
also in my Blackboard notes. You have to go to 3 point. It's in the first week.
What section is? Because I was trying to look at it, I didn't see it.
You don't see it now?
Is it on 4.1 or 5?
No, it's in week 1.
Oh, week 1. Okay.
No, I'm sorry, week 2. 3.3, week 2, 3.3.
Okay. Let me see real quick. I'm okay. I see it now. Thank you.
Okay.
Thank you, Professor. Have a great day.
Okay. You too.